Hey everybody, this next video lesson is going to cover the topic of periodic trends. The periodic table is set up and specifically designed to be able to be used as a tool. And as a tool, it has a lot of predictive properties to it. The first of which is a periodic trend known as the valence electrons. Now, first of all, we need to establish what the valence electrons are. Now you might remember this from a previous science course, but the valence electrons are the electrons that are located on the furthest energy level from the nucleus. If you remember, the nucleus is surrounded by these rings, and each ring can hold a certain number of electrons. Some of you might remember that the first ring can hold 2 electrons, and the next one holds 8, and then the third one can hold 8, and so on and so forth. The valence electrons are the electrons that are located on the furthest most energy level from the nucleus. Here you see 3 different elements all located in the first group of the periodic table. If you remember, these are the alkali metals. Now what I've done is sketched out the electrons as they exist around the nucleus of these 3 elements, lithium, sodium, and potassium. Now what you see is that in the valence energy level for lithium, which is the second shell, there's only 1 electron. Now in sodium, which has 11 total electrons, the first 2 are in the first shell, then I just wrote 8, meaning there's 8 electrons in this shell, and then 1 in the last shell. And in this final one, potassium, 2 in the first shell, 8, followed by 8, and then again 1. Now these 3 elements are stacked on top of each other on the periodic table, and you'll notice that they all end with 1 valence electron. This is a predictable pattern. In fact, the periodic table follows this predictable pattern. Every time you move a group to the right on the periodic table, you add 1 valence electron to the outermost shell. Regardless of how far down the group it is, each of those elements in that group share the same number of valence electrons. Again, here's a quick sketch of the periodic table. In the first group, as we already determined, the number of valence electrons of all these elements is 1 VE for 1 valence electron. And as I move to the right, I add another valence electron. So the second group of elements all have 2 valence electrons. I'm going to skip this section. The transition elements, they have unpredictable valence electrons, which is why we only stick to the main block. So over here, as the main block continues, this is boron, and boron and all the elements underneath it have 3 valence electrons. And this continues going up as you go across each group until eventually you get to the noble gases, which have 8 valence electrons. Now helium doesn't fall in this pattern because helium is up here and doesn't have 8 valence electrons, but its first energy level is full with 2 valence electrons, which is why it's listed with the other noble gases. These are all full, with their highest energy level having maximum number of electrons. But the 8 valence electron trend starts at neon and goes down below every other element underneath that. So in other words, if I just ask a random element, I say, how many valence electrons does, say, sulfur have? Remember, sulfur is number 16 on the periodic table. And since sulfur is 16 on the periodic table, and it's found just underneath oxygen, it has the same number of valence electrons as oxygen. And since I know that the noble gases have 8 valence electrons and oxygen is 2 groups back, then 8 minus 2 is 6. So sulfur, like oxygen, has 6 valence electrons. The next periodic trend that I want to tell you about is something called atomic radius. And it basically is the size of an atom. Atomic radius is defined as the distance from the nucleus to the furthest electron away, or in other words, the furthest valence electron. Take, for example, lithium, with 3 protons and 3 neutrons and 3 electrons. Now the first 2 electrons lie in the first shell, and the second shell has 1 electron on it. The radius in this case is defined by the distance from the nucleus to that furthest electron away. Not all elements have the identical atomic radius. In fact, elements vary in their atomic radius. Even though they're very, very small, they all are slightly different. This is a list of periodic table of elements, and these are the atomic radii of the elements. As you'll notice, we don't have the transition elements here in the middle. You can see by this gap. We also don't have the noble gases. Now, I don't know why the noble gases aren't here, but they're not. Now, atomic radius is a numerical value. As you can see, each one has a signed number to it. And I've given you a little bubble of different colors to kind of show the relative size of each of the atomic radii compared to the others. Now, we're going to compare atomic radius vertically with elements in the same column, and we're also going to compare atomic radii horizontally with elements in the same period. Let's first talk about elements in the same column. If you compare elements in the same group, what you'll notice is that the elements get bigger as you move further down on the periodic table. The question is why? Well, this should make sense to you because as you go down, remember we talked about how each time you go down you add a ring or a valence energy level, and every time you add a valence energy level you get further from the nucleus. So it makes sense that as you add an extra ring, you get a bigger atom. Now let's talk about the horizontal comparisons between atomic radii. As you can see, as you move from left to right, and I've grabbed a screenshot of the third period of the periodic table here. As you move from left to right, they get slightly smaller as you move to the right. Now this isn't exactly what you'd think it would do. You would think as you add protons and add more electrons, the radius would get bigger and bigger and bigger. Because in your experience, anytime you add more to something, it gets bigger. But this is not the case with atoms. The reason why requires a little bit more explanation. Think about this. How many protons are there in a potassium atom? Well, the answer is 19 protons. But that also means you have 19 electrons. And those protons and those electrons pull in on each other, and they pull in and hold pretty tight. With calcium, on the other hand, you have 20 protons and 20 electrons. And you have more protons and more electrons, and we have more positives pulling on more negatives, you get a tighter connection, and a tighter connection means that the electrons pull in closer to the nucleus. This is again counterintuitive to what you think, because adding mass should increase the volume or increase the radius, but in fact as you add mass by adding protons and electrons, they actually pull in tighter and tighter, which means your smallest elements in a row are further down to the right, and your bigger elements are further to the left. So to simplify this, the biggest radius elements are further to the left and further down on the periodic table, making the elements in the lower left-hand corner the largest radius, and the ones in the upper right-hand corner the smaller. Now a question on a quiz or a test, I would only ever ask you to compare the size of elements in the same column or in the same row, and I'd also expect you to know why. So it's one thing to be able to know the trend, meaning biggest radius down and biggest radius to the left, but it's also important to be able to explain why. The last periodic trend that I'm going to talk to you about is called ionization energy, and it's defined as the energy needed to remove one electron from an atom. Now basically what you can think of is ionization energy is opposite of atomic radius. If something has a large atomic radius, their electrons are more loosely held, and the further they are away from the nucleus, the easier they are to dislodge. Smaller elements hold on to their electrons tighter, and so it's much more difficult to remove those electrons. So if it's difficult to remove, we say it's high energy. And if they're easy to remove, we say they're low energy. Basically, energy refers to effort. As it says in the notes, the trend is opposite of atomic radius. For radius, if the largest elements are to the left and down, then the highest ionization energies are to the right and up. Think of ionization energy in the case of sports analogies. Now, no matter what sport you're playing, if it's a ball sport anyway, or hockey, the goal is to keep control of the ball. If the electrons are the ball in this case, and the nucleus is trying to keep control of them, then you want to keep the electrons close to your body, or close to the player. If the electron is hanging out too far away from the nucleus, then it's easy to knock it away. Think of a football player running down the field. They don't hold the ball out to the side. They hold it up tight close to their body because it's easier, or it's less easy, or more difficult for the defenders to knock it away. Or maybe you're a lacrosse player, and you're running down the field with the ball in your stick. And you keep the ball close to your body, otherwise the defender's going to come in and knock it out. Or even soccer. You keep your touches close to your feet, because if you kick it too far out in front of you, the defender can step in and kick it away at any moment. Ionization energy, the ease at which an element loses its electrons. The bigger the element, the easier it is to lose, essentially the lower the energy. The smaller the element, the more difficult it is to dislodge the electron, and thus the higher the energy. Ionization energy is a quantitative value, and these numbers represent the ionization energies of elements, and what you can see is the rows and columns of the periodic table. Now what you'll notice over here in the noble gases, as you go down the column, the ionization energy gets less and less. And that should make sense to you, because as you go down, these get larger and larger, so it becomes easier and easier to dislodge. Or, as you move up a column, or up a group, the elements get smaller and smaller, and thus it's more difficult to dislodge. And because of that, you have an increased ionization energy. Now, relatively speaking, as you move from left to right along a period, the elements get more and more difficult to remove an electron because the elements get smaller and smaller. So to explain ionization energy, it's important to also note that the size affects the energy. Small atom, high energy. Big atom, small energy. Now it's true there's some variability in the ionization energy, like sometimes it goes up and then drops significantly, and those can be accounted for. And if you'd like to know more about that, you should take AP Chemistry or take a college chemistry course and you'll be able to explain that. But we're just worried about the general trend, the increasing ionization energy to the right and increasing ionization energy going up. Well, that takes care of this video lesson. Thanks for watching.